This activity is meant to make you reflect on the things that we just discussed about the block diagrams, controllers, and how a system is really put together in order to maintain and achieve control. So let's think about, despite the fact that it's still pretty hot outside right now, let's think about the problem of heating a house in the winter. So right now, the outside is cold and you want the inside to be a nice temperature. So what we'd like to do is look back at the block diagram that we just talked about and draw a control loop. And in this case, try to be specific about what goes in each of the boxes and what those signals are that are going between the different boxes. In the second part, I want you to kind of describe the logic. You already know how a typical thermostat works, so describe the logic of what makes that controller achieve the desired temperature inside the house. In part 3, go ahead and draw, essentially as a plot over time, draw what the indoor temperature would look like, assuming that the outside is some chilly temperature, say at least 40 degrees, and that you set your thermostat to 65. So what does it look like for the indoor temperature over time? And then finally, go back to those 4 different control goals and discuss whether or not this particular setup and whether a typical thermostat achieves our 4 control objectives. So go ahead and write those down, pause the video, chat with your fellow students, and then come back and we'll discuss. So I've made a copy already of the control diagram, essentially the block diagram that we have from the previous slide. And now we're going to customize this for our particular case here. So in this case, the reference, that's our desired temperature. Desired temperature comes in, that's what we would like our temperature to be. The thermostat is really not only the controller, but it's also the sensor. So it also has something that's monitoring the temperature inside the house and then turning the furnace on or off. So there could be a more advanced system where you can have temperature sensors throughout the house that communicate back to a central thermostat that does the control logic. But for the most part, we all have sensor and controller combos in our thermostat. So overall, the plant, the system that's operating, includes the house, which is really where the dynamics of the system are. And that's essentially the heat leaking out from the house through the windows, the cracks, and everything else like that. And that's modeled by this disturbance that we're getting. So this disturbance is the heat loss, and the actuator is the combination of the gas valve and the furnace. So that injects heat into the house. And then, of course, the sensor is reading the actual room temperature, and that sensor could also have some noise, and we haven't put that into the model here, but you could have put that in there. So in terms of our 4 control goals, the question is whether it's stable. So this system is kind of inherently stable. No variable is going to blow up. But not only that, it does achieve our second goal, which is the fact that it tracks our desired temperature. So for example, if we wanted our temperature to be about at 65, that it does a pretty good job. And the type of controller in this case is what we will call it, the community calls this bang bang controller, which essentially means it turns on and off. So it's an on-off type controller. So very simplistic logic, but it does achieve our desired temperature. So we achieve some sort of margin above and below, and it's going to kind of oscillate back and forth above and below that desired temperature. So the question is, does this operate in the environment of disturbances? And yes, it does. So we're able to still achieve our tracking despite the heat loss that's due to our disturbances. Our house is not perfectly insulated and it still works. And then the question about robustness is, does this work even if there are model uncertainties? And in this case, This very, very simple controller uses a very primitive model, which is essentially that heat goes in and then we lose some heat because of some disturbances. So we don't even model the house. Some more modern thermostats could possibly build a data-driven model about the house insulation and how it reflects sunlight and things like that. But by and large, these simple on-off controllers are robust because we install that same thermostat and do no calibration in many different houses, apartments, and so on. And so it's a very robust controller mechanism. But we could talk about some inefficiencies of this process. So for example, it could be that these tolerances above and below are not pleasant. So for example, it could be that your house gets too warm before it decides to start, or before it stops the furnace, or it could get too cold before it starts it back on. So there's a variety of different things that a more sophisticated controller could actually achieve.